Hello. We're going to talk about rotational kinematics. In Chinese, 转动运动学. Okay, so I'm going to start with a circle. So when we go around a circle, right? We go around a circle, the circumference, right? It's the circumference. 圆周, right? It's equal to 2 pi r. Right? It's equal to, this is r, and that's equal to 2 pi r. Right? Okay. So if you don't go around the entire circle, then you may be going for this angle theta. And that's called this arc length here, L. Okay. So L is an arc length, 无常, yeah. Arc length. Right. So in Chinese, this is 无常. Okay. So that's arc length. So we have L, it's equal to R times theta. And this theta here, it's called angular, it's called angle, right? Or angular displacement. Okay. So this theta here is in terms of, the unit is in terms of radian. Okay, it's in terms of radian. So when this is going around the entire circle, then you have 2 pi r here, as you can see. And then this will be r, and then this theta here will be 2 pi, right? Sorry, 2 pi, right? So when you go around one revolution. Yeah, so 一圈, right? One revolution, it's equal to 2 pi radian, right? So you should probably study this already in your math class, and that's equal to 360 degree, right? So that's different units, radian and degree, okay? All right, so this two are, right? So this one here is for theta radian, and this is for 2 pi radian, right? That's all. Okay, so that relationship is what we're going to be relying on, and let's continue in that. So let's say if I do delta L delta T, right? So that would be then equal to delta R theta delta T. And since R is constant, so I move the R out, so that becomes delta theta delta T. So then we're going to define this one here, call that one R omega, okay? And really this is a average term because it's over the time of delta T. So this one here, we call that average angular velocity. Okay? So delta L delta T is how much you travel in the delta T time, right? So that's your, in the UCM, this is the linear speed or the linear velocity. So here, you can see this linear, right? So this is a linear velocity, right? It's equal to R times the angular velocity, just like this is the arc, and it's R times theta. Okay, so I'm gonna erase some of this material here. So we're gonna summarize a little bit. So we have L, which is the arc length, which is equal to R times theta. So similarly, you have linear velocity, which is equal to R times omega. Okay, so sometimes we have the bar, sometimes we don't. Okay, but just be careful, what you are saying. So this is the angular velocity, and this is the angular displacement. Okay, and this is the arc length, right? And this is the linear velocity. Okay, so we are looking at this similarity, right? So we are looking at the similarity between translational, 移动, right? Or you can call that linear. Sometimes they use the term linear. So going in a line, right? Straight line between translational and rotational. Okay, rotational motion. Okay, you can see the formula are quite similar, right? So in fact, we're going to introduce the angular acceleration. So this is I mean not angular, sorry, it's a linear acceleration, right? So this is a linear acceleration. Okay, and that's equal to r alpha. Okay, and this alpha is the angular acceleration. Okay, so the unit here, this one here is radian, and this one here is radian per second. Okay, so this is, when I say unit, it means this SI unit. Okay, SI unit. And alpha here, right? Alpha is angular acceleration is radian per second squared. Okay, on this side here, that you should already familiar, this is meter, and this is meter per second, and this is meter per second squared. Okay, so you can see how similar they are, right? They're very, very similar. All right. Okay, so now we're going to extend this to the constant angular acceleration motion. So constant angular acceleration motion and the constant linear acceleration motion, right? So both of these are motion. So I'm going to kind of compare them. Remember, in this case, we have V2 is equal to V1 plus AT, right? Okay. So this side here we have omega 2, omega is not W, omega is equal to omega 1 plus A will become alpha, alpha T. T is the same, okay? And the second formula we have is X is equal to V0T plus 1/2 AT squared. So similarly, X is our theta. So theta is equal to omega 0T, right? So V0 become omega 0 plus 1/2 A become alpha, alpha T squared, okay? And the third one is a square one, right? So we have V2 squared equal to V1 squared plus A, 2 A D, right? So in here, the V2 become omega 2 square, V1 is omega 1 square, and plus 2 alpha, right? And this D here is basically your angle, right? So whatever angle you have travel. So theta, you can say theta, give a special name, but we're just gonna use theta right now. So here we could have used X2, okay? And then we have the V bar is equal to V1 plus V2 divided by 2, right? Okay. And so on this side, the V bar will become omega bar is equal to, so average, right? This means average. This bar here means average, this bar, right? It's called bar. This bar, it's called average. So that's equal to omega 1 plus omega 2 divided by 2, okay? So that's a similarity between the formula of constant linear acceleration motion and constant angular acceleration motion. Okay, so I think we're going to stop there for the day. And so just recall a little bit. So what we talk about today, it's the rotational kinematics. Okay, so we haven't talked about rotational dynamics yet. So next we'll be talking about rotational dynamics. Okay, and that's when the torque will come in. Right, torque is needed. Right, is needed to generate an angular acceleration, right? Okay, so we need torque in order to talk about the dynamics, but we're not going to talk about that today. Okay, so that's all we have. See you until next time. Bye-bye.